Hello and welcome back to the lab. Today on the bench we have a TG501A. This is one of the time mark generators for calibrating scopes and a few other things. Being the A variant, it is also very modern. This is the next one in the series of the 3 modules that I got from a viewer that I said I would go over for him. This one we're going to do the same process we did with the TG506. Going to throw it in, do a slight capacitor refresh on it, get it ready for the long run, then run it through a calibration and get it ready for its user. Here's the business side. Now, one thing that's real nice to see on this one is right here we have the 5 megahertz high stability crystal. So accuracy wise, this should be very accurate. Also means it's going to be kind of a pain in the butt to align, but that's a me problem. The 2 fuses, a couple capacitors we'll need to adjust, nothing major. On this side, we have the high frequency board, which will need to come out. If you've never disassembled one of these before, these lines don't come out. There's the blue one comes off, the black one comes off, and this whole board lifts out. Is relatively easy to service on the TGs, not like the PG. So we'll get that all squared away, and then we'll run it through an alignment. And at the end of the video, as we go through, if there's anything interesting that happens during the alignment, we'll give some highlights. If you are curious about doing an alignment on one of these in depth, what it takes, I have a video further back in the channel where I've repaired a couple of these, but I've also done an in-depth alignment video on one of these, all the steps, everything to look for. So take a look at that. So with that, let me get this top board out of the way, and we'll go from there. And this is why sometimes we don't have visitors in the lab while we're actually working. That was way more tear down than it needed to be to get to some caps to replace. The front panel has to be completely disconnected. Knobs come off. These lines are what go to the BNC jacks. This will give me access to clean up this switch pack, which will be good since we got it open. And this connector right here actually comes all the way through, plugs in here, actually comes through this hole, comes down and hooks in here. So I have had devices, computers, laptops, things like that puked out all over the bench, and the user comes up and very shakily asks, "Are you sure you're going to be able to get that back together again?" So it can get a little wild. Definitely a good idea for me to tear this one down. The grease is dry on this drum. Got to put a little lubrication on that. Plastic on plastic actually doesn't have a lot of friction. However, a little bit of plastic safe lube will go a long way to keeping it from wearing out. Let's see, what else? Just a bunch of TTL circuits in the back, nothing major. I did have to loosen off this back frame to get play in the frame to get the board out of there. It's a tight squeeze, but I should be able to get to everything I need to get to replace. Nothing needs to be replaced up here, which is good. Also, the orange, green, and yellow BNC cables, these Tex micro BNC cables, those are fixed into the filter. This is I believe this is a comb filter in here. Every single one of these holes is an adjustment for the 2 nanosecond and 1 nanosecond time marks. So those cables don't come out. They only come out on the one side. That's atypical for these cables. Nice pin interfacing right here for the display. So the display just pops in the front like that. Did have those 3 same size screws, 1 oddball on this one as well. I'm going to tuck this out of the way because I don't want anything to happen to the shielding. And I also don't want anything to happen to these inductors and this part of the circuit, because this is all the 1 nanosecond and 2 nanosecond and 1 nanosecond and 5 nanosecond time marks come from up here. So this is a very fast, very fiddly to align and calibrate section. So we're going to put that well out of the way so it doesn't get injured. Here's our troublemaker. I'll get some caps replaced. That's just a bit with a desoldering tool and a soldering iron. We'll throw everything back together, and then as per normal, let it run for a couple hours. Well, apparently I have been chewing up these capacitors doing restorations. So I had a bunch of these 100 mic by 50 volt caps, but this is all I'm down to. I've got enough to do this one, but I had to do a resupply. So this particular series is not destined for new designs, which means they're probably going to phase it out soon, but I just did a bulk order that'll keep me in stock for a while. So I will get into some parts storage and organization in some future videos about how I'm organizing the lab, because I am still organizing the lab. But it is getting better slowly, one day at a time. For right now, back to replacing caps. Okay, we have all the capacitors replaced. We're in the frame. I have not turned the unit on yet because we are experiencing this together. And if it goes sideways, I want it to go sideways on camera. Well, if I did my job right, it shouldn't go sideways. So, this is a TG501, so we need a BNC cable, and we also need a 50 ohm terminator. Should have one on the bench. Here we go. So I'm going to pump this into the Rigol real quick. I do not know where the positioning is on this cam switch. To lubricate the cam, I moved it around. There are no stops on that one, so I have no idea where it is. So the way I've got it set up right now is I have the variable off. Cam switch is in an unknown position. I'm just going to use the frequency counter on the scope to tell me where to set the dial. God, stuff is temporarily escaping me right now. So, camera's rolling. We have the scope up. Gonna hit it. No smoke. Let's see here. Slow this time base way down. Hey, we have a wave form, but I think we are running very slowly. Oh yeah, this is real slow. Let me turn this up. Get it someplace where we actually have some reasonable signal. There we go. I am getting time marks, and that is saying it is 200 hertz. Let's speed it up a little quicker than that. 1 kilohertz. Actually, very accurate 1 kilohertz. Hang on a second. Okay, we'll cut some of the glare off the screen. Sorry about the angle. That is going to be, 1 millisecond time marks, if I did the math right. So we have a very accurate 1.00001. Nice and stable. Now, this 0.01, I wouldn't take that as gospel due to the fact that this Rigol is not hooked up to the rubidium, and actually the rubidium is not on right now. So I'm going to need to let that warm up before we do the alignment on this. So really this needs to be set with a frequency counter with better digits. The time base in this scope, even though it is good, is not great. However, it will let us stare at this waveform for quite some time. So we'll turn off all the measurements because we don't need that. Blow this up a little bit. We have nice, good time marks, nice and stable. It's not moving around, at least from the way the scope could see. I'm sure it's moving a little bit, but the scope is, it's good. What I was trying to say is the time base in the TG is better than the time base in the scope. So as we can do gross, am I in the ballpark measurements with the scope, even this modern scope, the time base is better in the plug-in. So I need the rubidium back, or I need the frequency counter backed up by the rubidium to actually adjust that time base, because that gives me a better time base to smash it against. This all gets into stability and how many zeros, and we're into like 10 to the minus 12 in terms of stability. It gets pretty out there pretty quick. So I'm going to put the knob back on, let this thing cruise. I'm going to put the cases back on, let it really warm up. Make sure it's not going to have any trouble, and then I'll do an alignment on it, and this module will be ready to go back. Well, those new capacitors clear the side panel, but not by much. Okay, I have the DSA 602 fired up. We're going to use the 11A72, and I want to check make sure our high-speed plugins are working. All right, I have waveform on the DSA. Let me move the camera over there. All right, so now we're watching the DSA. We are going to crank this up. It's going to lose it, I'm sure. This is a sine wave, so we will set trigger level, come down, bring this up. We are triggering, blow this way up. Bring this. Let's see if we can't stabilize this. And we'll hit auto set, see what happens. That looks better. And we're at 5 gigasamples per second, and our time base is, does it tell me? Frequency is 200 megahertz. All right, let's kick it up one more. Here's 2 nanosecond sine wave. That's actually looking pretty good. Let's drop to 1 nanosecond. The 1 nanosecond button didn't lock in. That was the problem. We'll auto set this. Wow, way too long of a time base. All right, it didn't like that. Let's see. We'll turn averaging on to clean this up a bit so we get some measurements off of it. And 1.004 gigahertz sine wave. So looking very good, and with averaging on, that's cleaning up quite nicely. So this plugin's cruising without too much trouble. Actually, the high frequency aspect of this one looks a lot better than my TG. But yeah, nice and clean. We're going to let this run for a couple of hours, let it burn in, and just make sure it's not going to have any problems. As long as nothing eventful happens, we're into an alignment on this particular unit. So, but for that, time will tell. I'm going to shut the DSA off because it is a very warm scope, and it is warm down here in the lab. Kick this back over to the Rigol, slow it down a little bit, and we should be good. And for testing, for no other reason, we'll let it run at a megahertz. So we are at 1 microsecond time base, and I'm going to just let it cruise. Well, we can take a look at some of the stability of the TG501A. We are off by 2 hertz on 1 megahertz, and you can see 0.32 is stable, but we are bouncing between millihertz and a couple of hundred microhertz is what our deviation is. So very stable clock in a TG. The rubidium is well warmed up and locked. It's not, oh, it can't be synced to the 1 pulse per second because my GPS DO is off because my UPS went south. That makes that battery far more critical to replace in the short term. So we're using rubidium only stability, not GPS DO plus rubidium, but that is plenty stable for what we're looking for here. So everything's good. I am going to adjust the clock and do an alignment on this. This is just a before the alignment's done. I'll bring everybody back after the alignment's done, and we'll take a look at how it looks. This one's not going to be too hard to align because of the testing we did on the DSA 602 already. The 5 nanoseconds, 2 nanoseconds, and 1 nanosecond waveforms looked very good, so I won't need to adjust anything in the comb filter. Power supply and clock is what we're going to end up having to adjust on this one. So I will get that done. I'll bring everybody back, and we'll go from there. Okay, there is not much to do to align this thing. We have our test points here for 5 and 15 volts. And then I have to adjust this timing crystal, but I have to get at the timing crystal this way with some really tiny tools. So that one's going to kind of be a pain in the butt to do. But good news is it's not that far off. So I do need to validate the power supplies, and we will do that real fast. And then once I'm done, it's just checking the time marks. Obviously, we're going to sync this to the rubidium and lock this in. After we do that, I will check the time marks on the DSA just to make sure, well, we'll know the timing is good, but I'll check the highest speed, the 5 nanoseconds, 2 and 5, 2, and 1 nanosecond time marks for wave shape and things like that. We should not need to adjust anything. Those looked really good when we checked them previous. So here we go. Nothing fancy this time. I'm just going to use the 6500 to do the voltage checks. Don't need the 7510 for this, but I do, because we're adjusting the clock, I do need the rubidium stabilized frequency reference, which is now back up and running. I did have the I did get some batteries for that UPS. I had a UPS go bad, which took out my, didn't go bad, the batteries died. Took out my 1 pulse per second source and the time mark generator, or not the time mark generator, the time server that's running in the lab for a little bit. So I was down for a day while I ran out and got some new batteries for the UPS, and I'm glad I did, because I did not want you guys to have to hear the beep every minute reminding me that, hey, the batteries are dead. We're at 5.18 volts, so that is perfect. And we're at 4.93, so that, or 14.93, so that is within spec as well. So now I got to get a tool, get in this hole, and align the clock. What do I have that's going to do that? And also, because this is an oscillator, it needs to be low capacitance too. So, okay. This tuning tool was the one that actually worked. We have a metal tip, but a plastic shank. Nice big hex handle to grab onto. Was able to get in there, get that adjusted, and I'm kind of stoked about that. Let me show you. Here's our new time base at 1 megahertz. 1 microsecond period, so 1 megahertz frequency. We are bouncing around. Those last 2 digits of stability are the instability in the crystal of this particular unit. So the fact that they're jumping around isn't too bad, but the decimal place is here. So we're dithering around at millihertz on 1 megahertz. So very happy with the time base. It adjusted real well. I'm going to check the high speed waveforms, but I think we're about done. All right, I'm going to let the time arc generator cool off in a moment. If anybody is curious as to why warm-up is so important when doing a calibration, we have a pretty accurate frequency counter here. I'm going to switch this unit on. And as we can see, right now the frequency is tracking up. It's going to stabilize, and then it's going to start to track back down and it's already starting to track back down. So we're going to see where it settles off. The weird part about this is I did not have the service port covered when I did the adjustment. Obviously you can't. So, but that can add some capacitance to that tunable capacitor, and that can actually drag off the frequency. So I want to see where this settles out. I need to leave this on for a little bit and see exactly where we settle out. Are you going to see this watching it traverse a scope? Probably. Doing the frequency comparison, if you have a long enough time span, it's quite apparent what some of this stuff happens. But we'll see how close it gets. It's still well within spec. Very happy with this, and it's still even trending down. So I'm going to let this warm up for a little bit, see where it ends up. And we're still... Nah, we kind of settled off. Still not quite stable yet. So, but that is why warm-up is so important, because the gear's not actually in specification until it's warmed up. So... And yeah, we're even going lower. So where I thought it was done, it wasn't even done. So that's why some of the gear has that 30-minute warm-up time. Some of my gear has 3.5-hour warm-up time. The 184, it has a warm-up time of 6 hours if it hasn't been turned on and it's dead cold, because it takes that long to saturate the oven. Some of the frequency standards, and in a calibration lab, none of this stuff would be turned off. Like some of the voltage standards and stuff like that in a cal lab, they run 24/7, so they don't have the warm-up time, but they also don't lose some stability, because you can get some hysteresis in some of the references when they cool off and shut down that's permanent. So there's a lot of nuance going on when we do alignments, and we need this much precision. So... not unhappy with that offset, so this is plenty in spec, and it's even better than it was when it came in, because it was at it was off by 2 hertz on 1 megahertz. So we've got it off now by millihertz. So it's a really good clock, is what that boils down to. So let's just buzz through the high-speed stuff, and then this one will be done. Okay, we've got 5 nanosecond time marks. We're on auto set right now. And what do we have? All right. It's still saying not triggered. Our 5 nanosecond per division wave is good, because we have 5 nanoseconds per division, and it's scrolling pretty good. This is used by a step recovery diode, so on the higher speed settings, the waveform looks kind of funky. Here's our 2 nanoseconds. And we're not triggered, so we'll trigger. We'll hit auto set here, see what it comes back with. Well, our 2 nanosecond wave looks a lot better than our 5 nanosecond wave. 500 megahertz. What's our peak to peak? Add peak to peak. 1.3 volts. That's a good. That is a good amplitude off of one of these. Let's check the 1 nanosecond wave. So we're talking 1 gigahertz at this point. The 1 gigahertz signal is much lower amplitude than the rest of them, so that's why the scope didn't trigger as well. We have a 1 gigahertz signal to 3 decimal places, which is fine. And we have a 500 millivolts peak-to-peak output, which is also good. And it's telling me I need better than 2 millivolts into 50 ohms, so perfectly happy with that. Okay, we're on the other side of the unit, and these 3 capacitors, this one, and this one, are the ones that are in control of the 5 nanosecond time marks. So I'm going to see if I can clean this up a little bit, because really what it wants is peak amplitude. It doesn't say anything about wave shape. So I'm just going to tweak these a little bit, see if we can't clean the wave shape up, but I'm going to be going back and forth between these 3, being very careful with this toroidal transformer. So let's, I'm going to move you guys back over to the scope so you can see the effect I'm having, but this is the adjustments that I'm doing. Okay. Let's see what tweaking some capacitors is going to do. We lose a lot of amplitude doing that one. That's maximum amplitude. That's maximum amplitude as well. Okay, so that's our maximum amplitude. So I can't tune out this step, which is fine. I mean, it is functioning. Sorry about the camera movement. Because if we line up the peaks of the waveform, which is what's measured anyway, we are right where we should be. So this is working. Thanks for stopping by the lab and taking a look at this TG501A. this is ready to go back to its home and spread some accuracy into its owner's lab. If you guys would like to support what I do and help me make videos to keep posting to YouTube, there are links in the description to take you to Patreon. I also have a affiliates page where supplies and things like that that I use in the lab. There's a list. It'll take you to a website that's outside of YouTube. It's my website. There'll be a list of supplies and consumables that I use every day in the lab that you guys can order from Amazon. The channel does get a small kickback. Everything that does go into the channel gets used in the lab. So it's everything that comes in is to make more videos and better content for all of you. As always, I am in the comments section between videos. More is always on the way. And if you like what's going on, subscribe and stick around. With that, I will see everybody in the next video. Bye for now.